Hi. Um, this section we are going to talk about thermal equilibrium. That is when a hot object and a cold object brings together, there will be heat transfer, right? Because you can remember that heat flow when there is a temperature difference. Then the heat will continue to flow from the hot object to the cold object until the hot object becomes cooler and the cold object become warmer, and then at the end they will reach the same temperature. That we call it thermal equilibrium. That is been mentioned before and you should have heard. In that section it is a bit different from what we have dealt with before, because beforehand we always use Q equals to power times T. Okay, there is usually some kind of energy provider which give out energy at a fixed rate, that is fixed power, and then wait after some time, then energy is calculated this way. However, when we talk about thermal equilibrium, that's not the case. We doesn't need to have a heater or an energy provider, because energy flow occur naturally between different objects that have a temperature difference, of course. So what does it mean? It means there is energy transfer happening right under our nose, in front of us. For example, if I use black to circle this object A, do you observe it is at a higher temperature at the beginning and the temperature dropped to a lower value? There is a delta T here, change in temperature from high to low. So we can already calculate how much energy is lost during this process. Q equals to mc delta T. Okay, using the mass of this object, the C, specific heat capacity of this material, and the delta T, the amount of temperature change of this object A, we can already calculate how much energy is lost by object A. And if there is no energy loss to the surrounding, for example, let's say these two objects touch each other. In real life, some heat will go from one object to the environment, to the air, or to my hand. Not all the energy is transferred from one object to the other. However, if theoretically it can be, let's assume there is no energy loss, then by the conservation of energy, the energy lost by the hotter body, which is the object A in the above diagram, is equal to the energy gain by the cooler body, the colder body. So have a look here. If now I circle the object B, okay, and then this time you observe the thermometer here, it is at a lower temperature. Okay, after they are in contact, heat flow from A to B, and then the temperature of B rise. So there is an energy gain of object B. The temperature delta T is positive this time. Okay, the delta T of object A is negative because from higher value to lower value, so it is a negative change. For B, it is a positive change. And the amount of energy lost by A, since we assume that all the energy from A goes to B, nothing is lost, so we can have this result. Okay, energy loss of the hotter body is equal to the energy gained by the colder body. You might think that is not so difficult to understand, but what comes by deduction after this conclusion is we can calculate the final temperature when two objects, two liquid or two solid, or some liquid and solid mixed together, the final temperature can be calculated. Okay, so these two yellow boxes is the assumption, and the conclusion after we assume that there is no loss, and then we can have a look how to calculate what we just mentioned here. So this agrees with the laws of conservation of energy. 能量守恒定律. That means that in a closed system, 一個密閉嘅系統, there is no energy gain and no energy loss in a system that there is no energy exchange between inside the system and outside the system. Then the total amount of energy is always conserved, does not change. Things can either convert to other form. For example, when I clap my hands, kinetic energy change to sound energy. It can change format, or it can flow from one object to another, but never destroyed, never created. That is the conservation of energy. Okay, so when we imagine there is two cups of water, one is hot, one is cold. What happens when we pour one cup into the other? That comes example 5. Should we discuss this school question? Calculate the example first. Okay, so have a look here. Remember, energy lost by the hot body is equals to the energy gain of the colder body. Okay, that is the key of this part. So have a look. Water. Water means 4200 joule per kilogram per degree Celsius, and then mass m 等於 0.5, and then the initial temperature of the water is 90 degrees Celsius, hot water. So, and then how do we treat it? We add it to another cup of water, of course, of mass 0.2 kg. MB 等於 0.2 kg. Let's say this is MA, this is MB. Okay, but this time the water is at 15 degrees Celsius, so it's very cold. And then what the question asks us to find out is find the final temperature after the water is mixed together. Assume there is no energy loss to the surrounding. Okay, and we use 4200 for water. And let's use what we have just learned already. Okay, so the energy loss of hot water is equals to the energy gain of cold water. Okay, that is because the conservation of energy assume there is no assume there is no heat loss. And okay, and since we have learned Q equals to mc delta T, we know the energy loss of the hotter body is equals to, let's name it Q1 and Q2. This is the energy loss and Q2 is the energy gain. And Q1 would equals to the mass of object A. Okay, QA and QB, like this. Okay, mc delta T of A and mc delta T of B, because each cup of water have their own mass, specific heat capacity, and change in temperature. But we do not know yet what is the final temperature. So let the final temperature be T. Sorry, I forgot this part. Let final temperature be T. Okay, and then let's see what is happening. The hot object is at 90 degrees Celsius, while the cold water is at 15 degrees Celsius. At the end, these, due to energy loss and due to energy gain, these two bodies will arrive at a mutual temperature when they reach thermal equilibrium. So when we let this temperature be T, we can calculate. How, you would ask? By writing the delta T. This is 0.5 here times say 200 times, this will be the initial temperature higher value minus the T that we do not know yet. And then here mass B is 0.2 kilogram. And this is also say 200. But this time, because the temperature change for B is indeed T minus 15. Okay. Then we have the two expression written out and obtained our equation. So the next part is to solve this equation. This is a mathematic problems, but I can tell you a technique because this part involves T, and if you have to distribute everything into it, then you'll get many terms. So a more clever way to deal with it is eliminate the numerical values first. For example, you can see say 200 can be cancelled out directly, and then this is 5, this is 2, so you can have like this 5乘90減 T 就等於2乘 T 減15. Okay, much simpler. And then with the help of a calculator, 5T, 2T, and then this 2T can be converted to minus 2T. Sorry, I should write every step for you. Give me more spaces. Okay, I write every step. 5乘90減 5T 就等於 2T 減30。咁跟住呢，有 T 嗰啲嘢就擺埋一邊。咁所以呢，就係 7T 就飛咗過嚟，負5飛咗去呢邊，負30就去呢邊，所以5乘90再加30，T 就等於幾多除7呢？5 9 45加30，480，咁就等於480除7就係68.6 degree Celsius free Pacific. Okay, have a look here. 68.6, correct. So energy loss by hot water is equal to the energy gain by cold water, and then you obtain the equation and then simplify them and then obtain the final value. Finally, you have to write a sentence to conclude because you have let, okay? And then therefore the final temperature is 68.6 degrees Celsius. Full stop. Then this is part A. And part B. The final temperature is measured to be 65 degrees Celsius. Compare this value to your answer in A and explain the differences. The final temperature, it means the measured by the thermometer, it is 65. However, we estimate it should be 68.6, right? 68.6 is 3.6 higher. But why do we measure in real life a lower value? This is because the room temperature have a play in this circumstance, because some energy of the hot water and the mixture is lost to the surrounding. 68 is still a quite high value of a temperature. If we are in a room temperature of 20 or 30 degrees Celsius, then this kind of high temperature is very easily lost to the surrounding, to the air, to the environment, to the table, to the container, and so and so. So the reason for the answer to be lower than in real life is because of energy loss. Okay, so you can have a try. There is another question which is designed in a similar manner, and let's try it out. For example, here there is also a hotter liquid and a colder liquid. And for the hot one, it is 2 kilograms. And for the cold one, it is 5 kilograms. This time, it tells us it is liquid and same liquid. So the specific heat capacity would be the same. So let's assume it is C. And it means it can be cancelled out. Okay. So what is the final temperature? Final temperature. Okay, so this time don't forget to let the final temperature. Okay, let me get my pen. Let. I should use black. 唔好執着埋啲無謂嘢啦，網上。Okay, let the final temperature be T, and then energy loss of hot liquid is equal to energy gain of the cold liquid. Energy gain of the cold liquid duplicate, put here. Okay, and then M1C delta T1 is equal to M2C delta T2, and then C is cancelled out. Delta T1 would be 80 minus T, and then delta T2 would be T minus 30. And sorry, I forgot M1. M1, the value of M1 is 2 kilograms. The value of M of 2 is 5 kilograms. Okay, so this is the equation we have to solve, and it is similarly easy. So 160減 2T 就等於 5T 減150，然後呢就係又係 7T 喎，就會等於160加150，即係310啦。 咁 T 就等於310除7就會等於310除7就係44.3 degree Celsius 3 sig figs. If in the test and exam you are asked some answer but you have many digits, then you should get 3 significant figure. Okay. Finally, 答題 final temperature is 44.3 degree Celsius. That is how you do this type of question. Okay. Summary. When you have objects of different temperature, they will have temperature, they will have energy transfer, and they will finally reach the same temperature. This is due to the heat exchange. And if there is no energy loss, you can make use of this yellow box here. Energy loss by the hot object is equals to energy gain by the cold object. And then in these two examples, you know how the process to calculate it. And then let's have a look at this box. Why should the experiment be carried out quickly? That is, okay, I let you think about it for a moment. Measure the mass and temperature of a cold water mixed together. Okay, do you know why it should be quick? Usually about the experiment, when we are asked to perform in a certain way, it is related to the accuracy. This time is no surprise as well, because the energy will be lost to the surrounding. If you perform it quickly, then less energy can escape within a short time. Okay, so if you can pour it quickly, stir it quickly, and take the accurate temperature measurement quickly, then you can reduce the error. Number 2, is the energy gained by the cold water exactly the same as the energy lost by the hot water? In theory, it might be, but in real life, usually not, because the cup will absorb some energy, the thermometer will absorb some energy, and the environment will also absorb some energy. So this yellow box is about correct, but in real life it is less ideal, and there will be a percentage of error happens because it is not a closed system. When it involves other apparatus and the environment, there is a heat exchange between your system and outside of the system. It is no longer a closed system. So the law of conservation of energy cannot fully apply here. That is why. Okay? If you have any question, you can ask me. That is all for this part. Usually this would be the more complicated and difficult type of question you will be asked in the test or exam. If even more difficult, it can only be like some energy loss involved and you have to explain something like that. Okay, that is all for this section. Thank you.